Hey. Okay, so couple of quick reminders and announcements. So there's another ICA out there. Just keep saying that there's going to be like 12 of these, but they drop below a 7, so you only have to do 5 over the semester. That ICA before lecture C1, which I think will be next week. I think it's probably Tuesday. I'd have to do that. I forget how many Bs we have, so it's either Tuesday. I think it's next week. But the due date is on Canvas. Homework B1 is available in Canvas. Individual assignment due soon. Preferably, we need to make it easy for the grader to grade and try to communicate sort of effectively. So one document, preferably typed if you can, in an electronic legible format. Responses should be kind of in a logical order. So question 1 comes on the first page, question 2 on the second page. If you can do it, in Word or even in LaTeX or something, that is going to be preferable. It's going to be easier to read. But in general, if the grader can't find your answers, or we're not going to take off for grammar or anything like that. But if your answer is not clear because it's not able to be found, or it's in sort of a funny location or something like that, have points taken off for that. So just make sure that it's clear in your submission. Kind of the big thing that I'm getting at here. Other things here. Let's. I have to focus this back here. Now. All right, so some clarifications here. So for question 1, it's kind of similar to your limit. I'm expecting at least 2 examples of each category. So if I'm asking for, what are the entities in this particular model, when do you give me 2 types of entities? Now, if you're having trouble trying to think of 2 types of entities, a lot of times you can just break your entities down into smaller groups. So if you are tempted to sort of say, well, an animal is an entity, well, there are a bunch of different types of animals. And so if you're modeling a zoo or a veterinarian office or something like that, then maybe instead of animal, you could say, well, dogs and cats. Those are 2 different entities, and then you're done. So like if you're an airport, passenger is one entity choice, but you could break that down into priority passengers or business passengers or economy. So if you're having trouble thinking of the different types of entities, then think about the entity group that you found. Can it be refined? Maybe it's too coarse. This is an alternative to differentiating by attributes. So in a real model, maybe it will be better to just have the coarsest level of entity and then they have different attributes later. But for the purpose of this assignment, if you're having trouble coming up with that second category of entity, then you need to break your entities down into more refined groups. In question 2, you use the state variables as defined around table 3.2 in the textbook. Just to summarize that here, LQ is the number of customers waiting for service, the number of customers in the queue at the time. LS, and we'll actually see an example of this today, is the number of customers currently being serviced. So they're the ones actually in the server. So as well, I think I'll hint here, LS is only ever going to be 0 or 1 for the homework example because there's only one server. Only one customer can be served at a time. There's also these cumulative statistics in D, S, and F. In D is the number of customers who've departed by that time. S is the sum of response times of all customers who have departed by that time. So if the response time is the total time that customer has been in the system from when they arrived to when they finally departed. So whenever you get a departure, you add that response time to S. Now it's easy to keep track of, but the idea here is if you divide S by ND, you'll get the average response time across all of the departures. So that's the reason why we keep track of that cumulative over time. And then F is the number of departed customers who spent 5 minutes or more in the system. So that's going to be a count. It will always be less than or equal to ND. And you only increment that if a response time is greater than 5. So if the passenger managed to enter, or no, the customer managed to depart 4 minutes, F stays alone. in 6 minutes or 5 minutes or more, then F is increased. So that's what we're just sort of saying here. So that's the definition of those 5 state variables. For those of you who started working on it, are there any questions about this? Pretty clear. Okay, good. There's the missing interarrival duration at the start of the interarrival table is not a mistake. So as we'll see in our example today, then the passenger, I keep saying passenger, the first customer is assumed to start into the system at time equals 0. So they don't have an interarrival time in front of them. So that's why there's kind of a gap. So as we'll see in the example today, the service time that doesn't have an interarrival time above it is how long that first customer takes to get their service. But then the next interarrival time is sort of the space in between customer 1 and customer 2. So it is not a mistake that there seems to be a gap in that table where there's no leading interarrival time. That's intentional, and we'll see that. Some hints here, the future event list will only ever have one arrival event notice, and that's because there's only one arrival process and only one server. So you only ever schedule one arrival. If you look at your FEL and you see more than one arrival event, then somewhere you've probably done something extra, or you forgot to get rid of an arrival event when you were supposed to. So we'll maybe we walk through the example. The FEL will also have no more than one departure event. No more than. So it's possible to have no departure events, but if you have 2 departures, you probably scheduled extra departures, or you forgot to take a departure off the FEL as you're moving. The clock will always match the time of the first event record. And so we'll see this in the example we do today. If your clock has a different number than the first event in the event record, then you might have, for example, forgot to take the event record FEL when you were moving ahead. Other things, LS plus LQ will always equal the number of customers in the checkout line. The checkout line has always got the customer being serviced at the head of it, and then everyone else waiting after it. So if you add those 2 things together, it should add up to that line, that length. The cumulative statistics, they're cumulative. They will not be non-decreasing. So if they decrease from one time step to another, probably something wrong with the logic. F is always less than the number of departures, and the response times jumps in S will be larger than the corresponding service duration, or it could be often larger, and that's because of the wait times. So this S you're not adding the service times. You might add the service times, but you're adding the service times plus how long that customer waited. So that particular customer, as they depart, they might have only had a 2-minute service time, but if they waited for 3 minutes, then their response time is 5, and you'll have to add 5 to S. So if you notice the jumps in here are ever smaller than the service times, or are always exactly the service times, then that probably means you're not calculating that S correctly. So just sanity checks. And then if you do the bonus, which is basically to implement the discrete event system simulation with a logic in Excel, and I give examples on how to do that. I'll actually do that in the next lecture, but I also have a video online showing how to do that, or at least some additional resources online showing how to do that, and the textbook talks about how to do that too. If you do the bonus, of course, bonus answers should match the hand simulation answers. And so if they don't match, then either there's something wrong with the bonus or there's something wrong with the hand simulation. So those are your sanity checks on question 2 there to make sure you've done the hand simulation correctly. So any questions about the assignments or difficulties? No questions online? All right, good. Okay, so just the Arena Rockwell competition, this is an option for your final project. You don't have to do it, but if you would like to have a shot at participating in this, the first, second, and third place, this is a national competition. There's a monetary prize. The entry forms are due at the end of September. So if you're interested, You have to come up with a group of, I think they would say 3 total students to submit that application before the end of September. Again, if you're looking for access to Arena, for information about different ways to get to that, I think you have to update that link there. So I'll go ahead and do that after this class. But if you look on Canvas, all the updated links are there. And also there's other competitions that I'm happy for you to maybe consider, but the trouble like with this competition, it uses FlexSim. So FlexSim is a competitor to Arena. Everything you learn in this class is easily generalizable to FlexSim, but you won't have as much support if you do this FlexSim. But if you're interested in healthcare, if you're interested in learning an additional software package, anything you learn in this class, it's easy enough to find the analog in FlexSim. So that would be another option. And then there's also additional, like Simio, another competitor, they have their own annual competition. So they all have got these competitions to encourage students to learn their software. And so if you would like to participate in one of these, you could use those instead of your final project. Otherwise, if you want to forget about this, that's fine. And you can just choose a system locally that you have data with. So none of these are required, but I'm just putting them out there as options. Okay, so last time, we've been further defining DES. So let's do a couple of examples here. So sort of modeling here, this as a crosswalk, as a discrete event system simulation here. And we'll see here that there are a limited number of resources that are keeping a lot of things waiting. So we can drill down into that and we can say, well, what are the interacting processes in this process-centric DES event? Well, there's cars on the road. So there's a process that's generating car arrivals and departures. And those cars, in order for them to go from arrival to departure, they need to cross the crosswalk. Likewise, there are bikes on the road. Similarly, bikes are generated on the bike paths as well as on the roads. And in order for them to enter and depart, they may need access to the crosswalk. And there are pedestrians on the sidewalks. They too may need access to the crosswalk. So all 3 of these things are being generated at random times, or effectively random, modeled random times. And in order for them to do whatever they need to do, they might need access to that crosswalk. And so that crosswalk or the road or the sidewalks, anything that they need access to in order to keep moving that another entity might be taking up at a time is a resource. So we could say the crosswalk is a resource. We can say the road is a resource. We can say the sidewalks are a resource, because those resources have a finite capacity. And once that capacity is full, the only thing you can do is sit and wait in order to get access to that. And so that's kind of how we would model this thing here. So each process generates entities that compete for resources. And on top of that, entities can contain resources. So when we start going into Arena, you'll draw process blocks. And when you drill down into those blocks, you'll be able to say, for this process to run, I need every one entity that goes through this process needs one of this resource. Well, you can have another process block named something totally different in another part of the model, and it too might need the same resource. And if one process block is using that resource, entities that arrive at the other process block will queue up, waiting for that resource to become available. So the processes themselves via using the same resources. So that's like this crosswalk here. This is one where all 3 processes need access to that crosswalk. And so long as there are pedestrians in the crosswalk, the cars and maybe even the bikes have to wait. So activities are the amount of time it takes for the pedestrians to get across the crosswalk, and delays are the time it takes for those waiting to enter the crosswalk in order to actually get through and start their activity. So a delay is the time you wait before you start your own activity, and activity is the time you take to actually use the resource. So that's an example with this. Are there any questions or need additional clarifications about this simple crosswalk example? They already see how there's 3 potential resources, how those resources can be used by multiple processes. Entities have activities, which is how long they wait when they use the resources. They have delays, which is how long they wait to use the resources. And ultimately, we know the activities ahead of time. So you could go across at any time of day and measure how long it takes for somebody to walk across it. You can get a distribution of time. But if then you were to ask, how long at 1 p.m. are you going to wait to get access to the crosswalk as a car? Then that's much more difficult. I mean, yeah, I guess you could go out at 1 p.m. and do that, but that's something that effectively you can't like build a model crosswalk in the lab and answer that question. You actually need all of these processes working together in order to answer that question. And so delays are outputs of simulations, activities are inputs to simulations. Okay. All right, questions online, clarifications. Okay. All right, so how do we, when we're starting a model, we have to figure out what are the entities, what are the resources, what are the activities, and so on. So I'm going to look at a simple example here of that looks like a queuing node. So those of you, when you eventually, if you haven't taken 470, you'll take 470 and you'll learn that systems can be broken down into networks of queuing nodes where you've got servers that have finite capacity that take a certain amount of time to serve things. And when the servers are busy, then things wait on them and there's queues. And that's sort of a diagram here. So this is the diagram for a queue. This indicates there's an arrival rate to the queue. This indicates there's a service rate with this average service time at the server, and this is a server. So that's kind of this diagram we'll see over and over again. And so if we look at this generic diagram of a queuing node, then we would say that the resource is the server. The activity is the average, or is the service time it takes to get through the server. The entities are those arriving to get into the server that might have to be queued up as they wait for it. And then the activities take time, and so the time spent in the queue is a delay. So that's kind of a generic version of anything you can model as a queuing system. Once you put it in this framework, it should be easy to find the entities, the resources, the activities, and the delays. Because if you can put it into this queuing node, the thing that sits as a server is the resource, the thing that's waiting in the queue is the entity, the time waiting in the queue is a delay, and the time the server takes to process each entity is the activity. So if you can put it in this framework, you can find those things. So let's think of more concrete examples. So there are different ways to shoehorn real systems into this framework where things that are entities in one perspective is in another perspective. So here I'm thinking about shipping examples where we've got shipping containers, we've got ships that shipping containers ride on, and we've got ports that load the shipping containers onto the ships and take them off the ships. So I can ask a question and I let the question drive my model. So in this question, I say, on average, how long does each container take to reach its destination? Now, when I read that question, what I should do is think, well, containers are flowing through the system, the ones being delayed by the ships that carry them. See, the question is asking about the experience of a container. It's effectively saying how much delay accumulates on a container as it waits to get on a ship and get wherever the heck it's going. So with that in mind, what do you think the entities, the resources, and the activities should be for this model? Any ideas? Also monitor online here. So what would be an entity for this particular model? Containers. Why are containers an entity? I heard containers from both sides. Yeah. They're the things being delayed. They're the things that arrive. You have no idea how long it's going to take for them to get through the system. They get through the system and they accumulate delay. So yeah, I would say containers are probably the entities. So what will we say are resources in this system? What are the containers waiting on? Yeah. So the cranes are kind of resources. So basically things at the port. So there's things at the port that are containers. Other resources that containers are limited, that containers need access to. What was that? The boats, the ships. Yeah, the ships and the space on the ships. So both of those things seem like important resources. And so if we kind of think of those things together, then the activities, those are, how long the containers take using the resources. And so for the cranes, that activity might be, how long does it take to actually, for an grab it and move it onto a ship? Well, we could measure that. Maybe it takes 5 minutes to pick up a heavy container, move it over, and place it on a ship. And then we could also say, how long are the ships? How long does a container use a ship? Well, I mean, that depending on what we're modeling. If we're modeling the whole, a whole transit route, that might be the entire time after the container hits the ship that it travels, and then until it's finally unloaded, and then that ship becomes available for another container to be loaded on it. So it kind of depends on, what we're modeling here. So the way I kind of broke it out here is I said, yeah, containers are entities. That allows me to track metrics based on container time. Ships are resources networked onto shipping routes. So then ports, in this case, we can abstract away into activities. And so we can say that the activity of loading, travel, and unloading, we can build that into sort of like the time it takes to get on the ships. Now, I can make a more refined model where ports are resources, but if I'm considering the entire shipping, where it might take days to get across the ocean, or longer, 2 weeks maybe even to get across the ocean, then the little bit of time it takes to get loaded onto a ship is probably not going to change my results that much. So in that case, I can just maybe take the time it takes to actually use the port and bundle it into the activity of making use of the ship. So, and that would make my model simpler. Okay, and that's kind of what I'm just saying here. I can sort of average away the little bit of time it takes to actually work at the port. So the port is a resource, but if I'm modeling a world shipping, then the time it takes for me to use that resource is so small, I can almost forget that resource exists. It's not the bottleneck. All right, so then I can look at another question. What is the longest duration a ship will stay at one port while loading and unloading? So this is the same system. Ships have got containers on them, but I changed the question. Now I'm asking about how long does a ship port while loading and unloading? So in this case, what are the entities? Check online. Ships are entities because they're the ones waiting. We want to analyze ships. We want to aggregate over ships. So yeah, ships are entities. What are resources? Docks, where the ships have to go. That's good. So that's good. And then the activity of using those resources. So if I'm going to break those down, I can say, well, ships, those seem to be our entities, maybe the containers too. Ports, so docks, ports, those are the resources that allow the containers to join with the ships, and the loading of the container is an activity performed by the port. So we can imagine a ship loads up to a port, and we know that every ship is roughly a certain size. Maybe that's an attribute of the ship. So for every size of the ship, we can say it's going to take this distribution of time to load it all up. And so we just can say that that's the time it takes to use a port. And once the ship's all loaded, it gets to leave the port and a new ship comes in. So we can model that. Any questions about either of those two examples? Okay, questions online? Questions online. Would you ignore the port time in any simulation? Or is it just simplifying it for the scope of the class? So that's a good question. It really depends on the question that you're trying to answer with the sim. So we don't want to make simulations more complex than they need to be, because then that's going to make them take longer to run. And in the end, a simulation with these tiny little activity times relative to the rest of the activity times versus a simulation that only has the big activity times may have even quantitatively very similar results. So I may not need to model all of the tiniest, activity. I might be able to bundle those all up together. Similarly, if you were like modeling the time it takes to make a sandwich at sort of a subway style station where you go from station to station to station, bread to lettuce to tomatoes to meat, you probably could just focus on how long it takes at each station. You don't need to worry about the time it takes to slide the sandwich from station to station. because that transport delay is negligible. Including it won't change your results. Now in a factory, where you've got the same sort of setup where you need to get though from station A to station B and it's on the other side of a building, now those transport delays are appreciable. And if you left them out, you might get very different results. So it's a complicated question. A lot of times what you have to do is when you're not quite sure, you need to build them out and run a pilot study and see if your models ever disagree. If your models do not ever disagree in your pilot study, then maybe you use the simpler model because it runs faster and you can run more replications of it. So it's going to vary, but ideally you want the simplest model so you can get the most replications or use the least amount of sim time. Hopefully that makes sense. Okay. Any other questions? All right, so the last example for this shipping one here. Will opening a new canal increase the number of ships unloading at ports per day? All right, so in this case, maybe I'll flip it and ask, what do we think a resource might be for this question? What is the major limiting thing in this question? The canal, that's right. So here we're saying, imagine a system with one canal or two canals. The canals never move. They're the thing causing the delay. So we know that canals will probably be the resource. Then we can ask, what's being delayed? Well, it sounds like the ships are being delayed. And maybe we don't care about what's loading and unloading from the ships because we're not focusing on that part of it. So I can see that ships are being delayed by a limited number of canals. So ships are my entities, maybe ports, but definitely canals are types of resources. And the canal operation, those are the activities. And so if you've ever sort of visited Panama, for example, and you were able to watch, or any canal actually, if you're able to watch ships go through the locks, you know that like it's a very different interaction than just watching a ship on open water. It is much more like, going through a series of steps. You have to kind of move into one lock, you got to wait for it to close, you got to wait for the water to rise, you got to move it. And so it takes a certain amount of time and a very predictable amount of time for a ship to get through those canals, unless there's a failure, like in the Suez Canal, and actually yesterday, if you saw it for a couple hours, another ship got lodged now. And so they had to unlodge it there. And so that's an example of a resource failing, like a machine failure. And we could simulate that. How often does it fail? Hopefully not very often, but when it does, it might take a long amount of time for that resource to come back online. And we can simulate that. So that's how we might model that, where the activity here is the average, the distribution of time it takes to actually get through the canal. And during that time, or get through each lock. And during that time, no other ships maybe can use that lock. So you're the only one, that ship is the only one using that lock. So it clears the lock rests, another ship comes in. So the locks themselves might be the resource. All right, any questions about that? Just sort of some practice here as you're doing your homework, B1, coming up with what are the resources, what are the entities, what are the activities. I could have gone on to what are the events, and I could say, well, in the lock example, like the instant the lock gets, fills to the highest amount. When the lock opens, that's an event. When a ship arrives, that's an event. So all of these things that change the state of the system are events. Okay. All right, so entities move in the model. They are usually moving in the real system, like cars going into car washes, customers going into banks, etc. It's not always the case though. Or generically, entities arriving into queues, servers, again, this is kind of like a bank example. Not always the case though. I gave you that weird example here where if you were to think of a vacuum cleaner, the vacuum cleaner limited source. The whole room is sort of wants access to the vacuum cleaner, but the room can't move, so the vacuum has to move to it. So even though the vacuum's moving, it is the limited resource. So when we model it, we often put ourselves in the perspective of a reference frame where the vacuum is stationary and the room is moving. And so in the model, the resource might be stationary. That's just generally easiest to do. Even in the real world, the resource might be moving around. So the key thing is not whether it's stationary or moving or not moving. The key thing is whether it's limited. If it's a limiting thing that you need access to get the work done, it's a resource. And that's kind of the key thing. And then once you isolate or identify the resource, then sometimes it's easier to figure out the entities. And you could say, oh, if the vacuum is the resource, the entity must be the dirt that arrives at the vacuum that then departs once it's been collected by the vacuum. The vacuum's got a finite reservoir for collecting that dirt. And so that becomes a resource. And once it's filled, then it needs to be emptied before more entities can be taken up into that, et cetera, et cetera. So, but sometimes defining the resources first helps you identify what are the entities. So if there's an obvious limitation, think resource first. Otherwise, usually it's easier to think entities first. So let the question or the stats help you pick the entities. Let the limitations help you pick the resources. All right, so any questions about that? Clear? Questions online? Okay. All right, so I'm not going to step through this example before, but this is where we ended kind of last time, is this car wash example where I said that our goal in doing discrete event system simulations is to have a method where we define activities and we define how processes relate to each other, and then we let the computer go and it generates an output, which is a timeline, which looks like a plausible timeline of events that could have occurred. And if you just know the activities and you know the process, you know how things connect together, then from there you could start out with an empty timeline, schedule the end of your simulation, and then you can walk through and generate every event that comes up just by drawing activities from these lists, drawing service times, et cetera. And as you're doing that, you'll accumulate gaps. And those gaps are gaps that are not described by the activities. They're not part of the input. Those are gaps that are interesting to us as operations researchers because they tell us where these costly delays accumulate. So now we know sometimes some cars are going to have to wait. They'll be readied into the car wash. Because we only have one car wash, they're going to have to wait for another car to get out of the car wash. And then we're going to say, is there another way we can organize the car wash to reduce these delays? It's kind of like if you think about if you're driving home from somewhere and you have the ability to order food from remote or something like groceries for pickup or something, you could say, well, I could order my groceries before I start my commute, or I could get to the grocery store and then do my grocery shopping. Well, if I stack things up so that useful things happen while I'm doing another activity, then it's going to reduce my delay. So if I know it takes me a half hour to get to the grocery store, but it also takes me about a half hour for the groceries to get serviced or the pizza to get made or whatever, then maybe calling ahead reduces my delay time. Even so, by changing the process, I didn't change the activities at all. I just changed the process. It stacks the activities different so that I get less delay. And that's really our job when we're doing these simulations, is to test out hypothetical changes to the system which cause the activities to line up differently to potentially reduce the accumulated delays. That's a big part of what these simulation studies do. So we can go through that and we eventually get our whole timeline out of that. So any questions about that? So that's all the old stuff. And I'd like to walk through an example nearly identical in structure to the second part of your homework today, so that we can all make sure we're on the same page about how to do these hand simulations. But before I get to that, any questions about the fundamentals? Questions online? Okay. All right, so this basically is going to be the setup that if you haven't looked at the homework, for the second question, you're gonna have a table that looks a little bit like this one, where you have customers up top, an interarrival row, and a service row. And customer one is going to take this much time being serviced. Customer two is going to take this much time being serviced, and so on. You can think of these as the time in between customers. So customer one is available immediately at the start of the sim. Customer 2 shows up 4 minutes after customer 1. So that's how we kind of interpret this table here. So even though they're lined up this way, you can really think of it as a list of inter-arrival times, a list of service times, and you just grab the next one off the front of the list as you need it. And then I also will provide an end time. So the sim will run until that end time. That will be the other thing that's provided. So given this and an end time, you should be able to generate a timeline. And that's what we do in the hand simulation. And this system, the process of the system, is a simple single channel queue with one server. So the idea is you've got, let's say, a clerk here or a cashier, and they take an average amount of time, that's what the mu is, to handle each customer. You've got customers that arrive trying to get access to the cashier, but because the cashier is busy, they have to queue up. And so that's what we're depicting here. So that's all I'm saying here. Got interarrival durations, service durations. We're going to use integers for all these just for simplicity, but in general, they're non-negative reals. And there is no first interarrival duration again. So that is not a mistake that there's a gap right there. All right, so that's the setup for the problem. There are state variables that we have to keep track of. So we have to keep track of at every time, what is the current number of customers waiting in the queue? Could be any number, any integer, or basically any natural number. So 0 through infinity. The number of people in the server at the cashier could only be 0 or 1. We keep track of, in this case, the number of departures, and which is any number from 0 to infinity, and the total response time accumulated across all customers, like I was explaining earlier. So response time is when the customer left the system minus when they arrived at the system. So it's their total time in the system. It's not just their service time. So every customer's response time will be larger than her service time. So customer 2 or equal. So customer 2 will have a response time of 8 or larger in this particular example. And the arrival time we can view as an attribute of each customer that we have to save. So we're going to see here, in order to calculate response time, when the customer leaves, we have to keep track of when they arrive to do that math. So that is our attribute in this system, the arrival time. So every customer, the instant they arrive, they get stamped with an arrival time, so we can remember that for future math. Now, as I mentioned on the homework, there's also an F, which is the number of customers that have taken 5 minutes or longer in their response time, but I'm not going to do that in this example. Okay, so the entities are going to be modeled as these little records down here. So where it's a tuple, where it's C and then a customer ID, and that just gets larger, like customer 1, customer 2, et cetera. And then the second thing in the tuple is their arrival time. That's their attribute. So that'll be whatever time they arrived at the system. So wherever the customer is represented in the checkout line, you're going to see this tuple will tell you who the customer is and when they arrived. And so that's how we're representing the entities, ID and arrival time. Any questions about any of this so far? This is just the setup of the homework, the second part. Okay, now those entities are going to be stored in this sort of, it's a state variable, but it's a list, which is called the checkout line. It's an ordered list. And the checkout line is just a list of entities. It looks like this down here, where the customer being serviced is always the leftmost, the first in the list. So this checkout line here, I would interpret that as saying that customer 2, who arrived at minute 1, is being serviced, while customers 3 and 4 are waiting for service. Customer 3 arrived at minute 2, customer 4 arrived at minute 8. So that's the way I read the checkout line. The length of this list is always going to be LQ plus LS. So if there's anything in this list, LS is going to be equal to 1. And then the remainder is going to be in LQ. All right, any questions about the checkout line? So we're going to have to every tick of the sim, we're going to have to update the checkout line. Okay. Events. So there are three types of events in this simple system. There's an end event, which is an artificial event that we generate that just tells us when to stop simulating. It doesn't exist in the real world. There's an arrival event and a departure event. Now, both of these are, all three of these events, the first, they're, in this case, it's a two tuple, and these are three tuples. The first letter just tells you the type of the event. The second entry is going to be a number that will tell you the time that the event occurs. And then the third entry is going to be information that is relevant to that particular type of event. So I don't need to know anything else for the end event. That's why it's only a two tuple. For the arrival event, I need to know who arrived. So it's going to be a customer ID. And for the departure event, I need to know who departed. So a customer ID. And all of those get put into the future event list, or the FEL. So this is an example future event list. The future event list should always be sorted by event time. So notice it goes 11, 15, 60. You may not add them in order. It might be that you thought the next event was arrival 15, but then you got the logic told you needed to schedule a departure, which happened at time 11, which means you end up having to add it to the left here. So you're always going to need to make sure the FEL is sorted with the least times on the left and the greatest times on the right. And as we'll see, the entry that's on the farthest to the left will be the entry that is sort of being processed. And so we'll see how that shows up here. So what this represents is the next scheduled event is a departure at time 11 of customer 3. Then after that, all that we know that will happen is there'll be an arrival at time 15 of customer 5, and then eventually the sim ends at time 60. Other events might occur, so you might continue to schedule things. I mean, there might be other things that will be scheduled between the beginning and the end here, but at this instant of time, at this clock tick, these are the only events we know will definitely occur in the future. So it's not all of the events in the future, it's all the events we know about at this time. And we get rid of the events we process. So any questions about this FEL? Questions online? So response time is the total time an entity is in the system. Yes, response time is the total time a single entity is in the system. It's equal to whatever their departure time is minus whatever their arrival time is. It is their service time plus their wait time. It's their activity time plus their delay time. Any other questions? Okay. So what do we do on simulation execution? Well, it's all going to be driven by the FEL. So basically, we're going to move to the next time in the FEL to get our events out. If we find that the next event in the FEL is an arrival event, so it starts with an A, of this particular customer, CI, then we look at the state variables to figure out what the logic will be for scheduling the next things and updating all the state variables. So we look at the checkout line. If the checkout line's empty, which will mean that LS plus LQ is equal to 0, that's another way to check that, then we know that in the real system, the arrival goes directly to the cashier or directly to the server. So in order to deal with that, we now can schedule their departure by looking at the service time. So we go up and we say for customer I, let's say it's 3. Let's say she arrived at time 6. We're going to add 1 to that to figure out that she'll depart at time 7. So it's the current time T plus whatever her service time was from the table. And so we'll schedule that event. Now that we've moved her into the cashier, then we need to say the cashier is busy. So we're going to increment the number in the server. So we can set LS to equal to LS plus 1, or equivalently, in this case, because LS is always 0, 0, 1, we just set it equal to 1. But generically, we're just incrementing this state variable, the number that are currently being in the server. Now, if the checkout line was not empty, so there already were others in there, then that means that this arrival has to wait. They can't get to the cashier. So what do we do in that case? We increase the number of customers in the queue. We add 1 to the queue, and we make sure that the customer is in the checkout line. So for both of these, we add the customer to the checkout line. Either the first position in the checkout line, if the checkout line was empty, or the next position. So, to the end of the checkout line. And then for both of these things, because we've processed an arrival event, we can't move on without scheduling the next arrival. So then we go up to the next interarrival duration, we add that interarrival time, and that puts our next arrival on the FEL. That's how we process an arrival event. And then we're going to move on to the next event in the FEL. So any questions about this logic? Does that make sense? Before we do the departure event. Questions online? All right, so what do we do in a departure event? So if we hit the departure event, then we say, well, one customer's departed, so we're gonna update this cumulative statistic, adding 1 to it. And then we need to say, we need to update this cumulative response time. And we just add to the existing cumulative response time, the current time minus the arrival time of that customer, which we know because it's part of the little customer entity record. And so it's the second element in the 2 tuple for that customer. We just grab that, subtract it from the current time. That gives the response time for that customer, and then we can add it to the current cumulative response time. So those are things we have to do for every departure event. Now at this point, we can remove that customer from the checkout line. So we take them out of the checkout line list, and we subtract 1 from the number of customers in the server. Now, it may be the case that someone else is waiting for the server. So if the checkout line after that point is not empty, so there's another customer waiting, we now add 1 back into that LS. So effectively nothing's happened with LS. We decrease 1 from LQ, and we schedule the departure event. So we look at this new CJ, this new customer J's service time, we add it to the current time, and that's when CJ is going to be leaving. So we schedule that in the FEL. And so this customer is the next one in the checkout line, and then the service time is the next service time from the list. That's what I'm just saying there. And that's all we have to do on the departure event. We don't have to schedule another arrival because we only do that when we process arrival events. So that's the whole logic for the departure event. Any questions about that logic? Process logic. Questions online? Okay. So then the easiest event to process, the end events. So if the next event in the FEL is an end event, we basically terminate the simulation at time t. And if we wanted to do any post-processing, like to calculate averages, we could do that then. I'm not asking you to do that for the homework problem, and so on this case, you just stop. You don't even add another line to the simulation table. So that's what I'll show you in this example here. So let's step through an example. And this is basically just like homework, the second part of homework B1, except there's no F here for simplicity. So you start out with an empty table, set up your table like this. The simulation table, and here we're going to say for this one, we're ending at time 15. Someone's really angry. So you can, for those at home, there's loud banging from the hallway. So I will give you a different end time. It won't necessarily be 15. I picked 15 arbitrarily for this problem, but pay attention to whatever's in the homework problem. All right, so first thing we do is schedule that end event. So we know that we need to populate this first row, and we know that the FEL is going to at least have the end event. That's the only thing we know that's going to happen. The first thing we need to do is put the end event in the FEL, and that guarantees that we will eventually end the simulation. So then the second thing we do is we know that customer 1 at time 0 starts into the system. So we can then schedule an arrival event for time 0 for customer 1. So basically we can say, I say schedule an arrival event, but really what it means is we're processing customer 1's arrival immediately. So I'm going to move clock to clock 0 to correspond to this customer 0's arrival. And I go through the process of saying, well, if we are here starting the sim processing customer 1's arrival, what does the simulation logic say we need to do with the rest of the state variables in the FDL? So this is an arrival event. So the first thing I can do is I can schedule the departure because I know that customer one goes directly into the server. And if I look up here, customer one, the service duration for customer one is only 1 minute, right? So that service duration that's only 1 minute says I'm going to take time 0, add 1 to it, and I know the customer one's going to depart at time 1. Now, because customer one is in the server, I have to update ls so that ls is now equal to 1, and I have to put customer one in the checkout line at the first position. First position is the customer being serviced, and then I need to put the schedule a new arrival for customer one, or sorry, customer two. So whenever you process one arrival, you schedule the next arrival. And so I look at the inter-arrival times, I see there's 4 minutes in between customer one and two. So customer one came in at time 0, customer two will then come in at 4, so that goes on to the FDL. And then the rest of the things here, I know are going to be 0. There's nobody waiting in the queue. Nobody's left. So these things start at 0. And I'm done with that first line. So that is this clock equals 0. That's me saying we're done. We can finally say that is what happened at time 0. Any questions about that first line? Yeah. Right, so that's a good, so the question is what, so you schedule the departure for 1, but what if there's a delay? Isn't it possible for him to depart later than 1? How does that accounted for? Well, the delays are a function of the interacting processes. So when we schedule a departure for 1, we know it's going to happen at 1. So we don't know when customer 2 is going to depart, for example. So so it may be the case that customer 2 will actually have to experience a delay. It just so happens that customer 1, because they arrived to an empty queue, didn't experience a delay. So the delays will happen organically through following the FEL. So if you happen to be at a point where a customer walks up to the server and the server is available, then you just say their departure is going to be whatever that time is plus their service time. And now if they immediately arrived when they encountered the server, that means they're not going to have any delay. But if they've been waiting there for 5 minutes to get to this instant, then that 5 minutes they've been waiting will be the delay. So that had already been accounted for. Does that make sense? And we will see an example of that in this example. Other questions about this starting here? Right, in some ways, the first line is the hardest line, and then everything else is just processed in the FEL. So you set the initial conditions up, and the system will run. So let's jump to the first event in the FEL. So that's this departure at time 1. So, and by the way, you don't have to put a timeline in your homework. All you're responsible for is the table in your homework. All right, so we jump to the first event, and we say, oh, the first event, time 1, that's a departure. Well, what do I do with departures? Well, I increment my departure counter. So it's going to go up by 1. So the next thing I do is I figure out what was the response time of the departing customer. Well, the departing customer was customer 1. Customer 1, if I look at their entity here, they arrived at time 0. So I'm going to add the current time 1 minus the arrival time 0 to the current accumulation of response times, and that'll bring it up to 1. And then I'm going to remove customer 1 from the checkout line, emptying it out totally. And then I say, is there, emptying out totally, is there anyone else left? Well, I can remove 1 from the server because I moved customer 1 out of the server. Because there's nobody else left in the checkout line, then I don't need to schedule any new departures. So that means that the server is going to be idle until the next arrival. So that's another type of delay, the amount of time a server is idle. So I'm done with that row there. I just emptied the checkout line, processed the departure, the cumulative statistics went up, the FEL got smaller, nothing was added to the FEL because that second arrival hasn't happened yet. That second arrival is not going to happen until the next line. Questions about that? Questions online? I see a question, if the server is a machine that breaks down, what happens to customer one? That's a great question. For this model, we have not introduced a failure process. In a more complicated model, there would be another process which would tell us the statistics of machine failures. So you could imagine there would be another line down here, which would say duration between machine breakdowns. And when I started the sim in the FEL, I would have to have a machine breakdown as another type of an event that was scheduled. And when the machine breaks down, I would have to have logic that would reduce the number of servers available, which would change how delays accumulate through the rest of the sim. So in a real system, machines can break down. In our modeled system, we are not modeling breakdowns, but if we wanted to model breakdowns, we would need not only an arrival process and a service process, we'd also need a breakdown process in a list of times corresponding to the time between breakdowns. And we will see that. You'll do that sim when you get to it. There's an arena lab where you'll simulate machine failures. Another question, oh, I guess it was an extension of that question. All right, great questions. All right, so now let's jump to the next arrival. So we're processing the first arrival here, A4. So notice the first event in the FEL always corresponds to the time on the next line. So this first event on the FEL, A4, is going to correspond to time 4 here. So we're going to jump to time 4. That's an arrival. What are the things we do in an arrival? Well, whenever you do an arrival, we say, is someone in the checkout line? If they're not in the checkout line, we move them directly into the server. How do we move them into the server? We schedule their departure. The departure is going to be their service time plus the current time. This arrival happened at 4. This is customer 2. Customer 2 has a service time of 8. 4 plus 8 gives me that 12. That's when the departure is going to happen. So I need to add this departure to the FEL. I will do that. I also need to then add 1 to the number of entities in the server. I need to then add the customer to the checkout line and schedule the next arrival. So I look to the inter-arrival times, 2 minutes between 2 and 3. I add 2 to the current time to get me the next arrival. And that should be all the things that I need to do. So now I'm done with time 4. So there I've had my new arrival, I have my new departure, my old arrival is gone, the end time carries through, customer 2 is in the checkout line being served, nobody's waiting. All right, any questions about that? We're seeing how this automatic process, how it goes. So what's the next type of event that we're going to process? Like, what are we going to jump to? What's the next event? Is it an arrival, departure, or an end? Arrival, that's right. So let's see that. We'll try to go through this a little quicker. So we jump to the next arrival. This is an arrival, but they arrived and the checkout line has already got someone in the server. So they don't get immediate access. So here's where the wait time or delay starts. So this is the first customer that actually has to experience a delay. And so we are going to increase 1 to the queue number. We are going to put that customer in the checkout line. We are going to then schedule the next arrival, because whenever you process an arrival, you always schedule the next arrival by looking at the inter-arrival times here. But we don't touch the service times because this customer didn't get access to the server, so we're not ready to start service. So that's all that we do for that time point here. And now that new customer 3 is starting to tick off delay. So they're sitting there because their service is not going to start until later. The difference between now and when their service starts is their delay. So the delay automatically comes out to how the activities stack up in this. So then we jump ahead to this next arrival, customer 4. They also are going to experience delay because they arrive and now there's 2 ahead of them. So we have to add 1 to the queue. So now there's 2 in the queue. We need to put them in the checkout line, so they'll be here in the next line. We need to schedule the next arrival, and then that's all we need to do. So now we have 2 customers sitting there waiting. We moved up to here, so there's 2 customers in the queue, 1 in the server. Finally, our next event is the departure of C2 that's holding those other customers up. So we jump to that departure time at time 12. Notice it's a big jump. Nothing happens in between that time. We increase the number of departures. We increase the cumulative statistics. So 12 minus 4, that gives us 8. So that's the same as their service time. They didn't have any delay. We remove them from the checkout line. We remove 1 from the server, but we're just going to end up adding that right back in just a second. So that's what we do. We add it back because C3 now gets access to the server. Because and then so we're going to remove 1 for the queue. Because C3 gets access to the server, we need to schedule C3's departure. So now C3's service time is only 1, but C3 had to wait. They arrived back at time 6. So it's currently time 12. So they had to wait a whole 6 minutes before they even get to start their service. That's the delay. So we update the clock. And then finally, the last, well, this will end up being the last line, as we'll see. The next event is the departure of C3. So we increase the number of departures. We look at their response times, 13 minus 6. I always hate to do math in public, but I think that's 7, 13 minus 6. And so if we think about it like their customer 3, they only took 1 when they actually got to the cashier, but they had to wait that extra 6. That's the delay. So we add that to the response time here. So we increase 7. So 9 plus 7 gives us our 16. Then we remove them from the checkout line, which is going to remove 1 from the server, but because this C4 is waiting, that's going to get added right back in. And then we remove 1 from the queue, and then we can schedule the departure of C4. Now, the departure from C4 actually happens after our end time, but you still add it to the FVL, even though you, as a human, know that you're never going to get there. It would be too costly for the computer to keep looking at the entire FVL every time it's adding something to the schedule. So it just schedules. It doesn't worry about when things are going to end. And when it ends, there may be things remaining in the FVL, and that's fine. So we're done with 13 here, and we see the end event is the next event. There's an arrival that happens after the end event. There's a departure that happens after the end event. But we're done with our sim table. So after we do the clock 13, we don't go forward and try to simulate E15 because nothing happens at the end event. We just stop there. And that is your submission. So if I go forward, I just jump to the end and that's it. So any questions about that logic? That's what you'll do in question 2 of your homework, but you'll also keep track of this F cumulative statistic as well. Very similar to what you were doing in the muffin sim in lab 2. Now notice the big difference between this and the muffin sim is in the muffin sim, there's an arrival every minute, but the number of entities that arrive every minute is where there's randomness. In this one, there's random durations in between arrivals, but there's only ever 1 arrival every arrival event. All right, any questions about that? Is it pretty clear or seem like something you could do? And again, I've got examples of this online. In fact, I think I've taken all of the past homework B1s, maybe a couple more, those solutions, and I put them in one big document. So if you want more examples of this, if you look on Canvas, there's linked up there, there's the solution sets for like all of the other ones from the previous semesters as well. So a lot of resources if you're still getting used to this. Okay. All right, so that's all I've got for you today. So if you have any other questions come up after, so let's just end with an attendance question. So I'll get my mouse back here maybe. There it is. So the attendance link there, 475 ATT. And the question I'll ask here is, what does LS plus LQ represent in the hand simulation? So what does LS plus LQ correspond to in the hand simulation? And that's all I've got for you. So like I said, if you have any other questions, feel free to come up. If I don't hear from you, have a good weekend. Remember, lab due on Sunday, and double check the due dates for the other assignments. Let me just stop the recording here. I2, here. All right, well, those online, I'm going to end the meeting now because Zoom has locked me out of my controls. So if you have any questions, feel free to send me a note.